Here we go. So last time we started this segment on optimization, basically finding relative maximums and relative minimums, and for functions of two variables. Okay, for functions of two variables. For functions of two variables, because I don't want to get into the D test for functions of three or more variables. It's a nightmare, and they don't cover it in the book anyways. So the idea is you first get your critical points, and that is done by setting your first partials simultaneously equal to 0 and solving a system of equations. And there may be more than one critical point, who knows? After you get your critical point or critical points, you perform the D test, also known as the second partials test. So you form this quantity known as D, which involves second partials. So you take fxx multiplied by fyy and then subtract fxy getting squared. And then you evaluate your D at the critical points. And then four things can happen, four possibilities. If D is greater than 0, you have to evaluate fxx. So if D is greater than 0, but fxx is also greater than 0, you have a relative minimum. If D is greater than 0 and your fxx is negative, you have a relative maximum. If D is negative, you don't have to check anything else. Just boom, you've got a saddle point. And if D is exactly equal to 0, it doesn't mean that there isn't a max or a min. It means the test is inconclusive and you may have to use like a computer-aided system or something to figure out what's going on. Okay. And we had time for one example last time, which I did for us. And it turns out after all was said and done, when we got the two critical points, we ended up with a saddle point right here. And we ended up with a relative minimum. So a saddle point and a minimum, no maximums. Now I graphed this surface for you just so you could see the minimum and maybe you can make out the saddle point. But this is the surface here, and you can see the minimum there at the bottom of that valley. And if I kind of spin it around a little bit, you might be able to make out the saddle point over the way, well, it's kind of down below, but so this is kind of an interesting looking surface. I could maybe make it look more rainbowy, so it's kind of pretty. But that is the surface that we were finding the extrema and the saddle points for. Okay, fine. So back to the matter at hand. I'm going to skip example 3 for the moment because I want you guys to have a shot at doing it. And I will do examples 4, 5, and 6, and then you're going to do example 3. Okay? So example 4 has a different flavor that from my first example, example 2. We'll see in a moment why. So please keep your eyes open for why is this problem different from the one I did last week. So here's a function of two variables. Great. Let's go get the first partials. And when we differentiate with respect to x, we get 4x cubed minus 32. When we differentiate with respect to y, we get 5y to the 4th minus 5. We simultaneously set these partials equal to 0. Now, I want you to look at this system of equations right here. Systems of two equations and two unknowns. Do you notice that each equation has only one variable in it, not two? Unlike the system of equations we got back here in example 2. Here in example 2, when we got the system of equations, both equations had an x and a y in it. This one doesn't, so it's a different deal. And so there's sort of different rules that apply that we'll see. So first I'm going to solve the first equation for x, because I can. And after dividing both sides of the equation by 8 here, and then I'll take the cube root of both sides like so, and I get x is equal to 2. Fine. When I do the same for the second partial, I'll add 5 to both sides, divide both sides by 1. And remember, when you take an even root of both sides, and I'm going to be testing you on this, and you'll lose a lot of points if you don't honor what I'm about to say, you always have to remember there's a plus or minus. Odd roots, no. Like when I took a cube root of both sides, I didn't have a plus or minus. even roots like square root, fourth root, sixth root, etc., you got to have the plus or minus. So plus or minus 1 is what y is equal to. Now here's the weird part. When you have a system of equations where each equation has only one variable in it, you mix and match to get your critical points. What the heck do I mean? I mean, when x is 2, y could be 1. And also when x is 2, y could be -1. So we have two critical points. There is a mixing and a matching going on there. Now what? I'm going to form the d quantity and then evaluate d at these two critical points. Okay, so d, which is fxx times fyy minus fxy squared. For us, fxx, I'm going to do this on the fly here, is the derivative of fx with respect to x, so that's 12x squared. Fyy is the derivative of fy with respect to y minus fxy squared. But fxy is the derivative of fx with respect to y, and that's 0. Okay, so there's d. So now let's test the point 2, 1. So what does that look like? Well, d evaluated at the point 2, 1 when you substitute in the coordinates here. I get some number. I don't even care what the number is, people. Like, I don't even punch some of this up in my calculator because I don't care. What do I care about? If it's positive or negative. And I obviously I get something positive there, some number. Okay, fine. What does that mean? Well, the D test says if D is positive, you're not sure what it is yet. You have to evaluate fxx at that point. And since fxx is 12x squared, and again, I don't care what the value is. I just notice, hey, that's positive also. What does the theorem say when both D and fxx are positive? What do we have? Relative max, relative minimum. Yeah, we have a relative minimum at the point when x and y are 2 and 1. And what's the actual relative minimum value? The actual, and some students get confused when they're asked about the actual min value. That's the original function evaluated at 2, 1. So you would punch that up into your calculator, and I get, what is the actual min? I think it's -60. Ooh, that's pretty down there. Okay, now what? Let's test the other critical point, 2, -1. So when I evaluate D at 2, -1, what happens? This is, I think I screwed up here. This was supposed to be 20. You guys didn't even say anything. This fyy is 20y cubed. What am I doing here? That's a cubed, and that's going to make a difference here. Why? Well, -1 cubed is negative. So this whole thing looks like it's going to be some negative number. Again, I don't care what the number is. All I care about is if D is negative or not. And when D is negative, you don't have to go and check fxx. You can immediately conclude that there is a saddle point at that location. And if they ask for the order triple, which I usually do, well, when I do face-to-face exams, I don't think my math lab does too much, but it looks like -52 is the Z coordinate on the surface of the saddle point. Okay, and we're done with this problem. So what we ended up with is a min and a saddle point again. And the difference was that the partials ended up being the kind of partials that don't have both variables in them. Any questions on this one? Okay, let's do a classic one. This problem is virtually in every single calculus book I have. Yeah, it's either in the text or the homework part. So all these calculus books over here, they all have this problem or something very similar to it, the same kind of flavor. So I love this problem for a few reasons. One, the nonlinear system of equations that we're going to get once we set those partials equal to 0 is hard. Yeah. And it's harder than anything that you've done in an algebra or pre-calc class when you studied nonlinear systems. They didn't do something this hard. So we're going to find out. If if you can handle it. And you can. It's not that bad. So I'm going to go ahead and get my partials. Here we go. Fx. Okay, when I differentiate with respect to x, I'm going to get 4y minus 4x cubed, and I'll set it to equal 0. When I differentiate with respect to y, I'm going to get 4x minus 4y cubed, set it equal to 0. Okay, so there is a nonlinear system of equations, and this is a true system where both equations have both x and y in it. So we're going to use the method of substitution to solve. You don't want to try adding these two equations together to eliminate a variable. That might work once in a while for nonlinear systems, but you usually not, because you can't add unlike terms to each other. You have to be careful. It would only work if you had like terms where something would be eliminated. So then what? Well, pick which of these equations that you want to solve for one of the variables and stick it in the other. And it doesn't matter because they're both equally weird. How about for the first equation, I'm going to solve it for y. So if I add x cubed to both sides and then divide both sides by 4, I get y equals x cubed. Great. And then what? I'm going to substitute that into the other equation. And that's why they call this the substitution method. So then what? So I'm going to have 4x minus 4 y getting cubed, and be careful here because you have to know your exponent laws. And this is where I see students choke, is they forget a lot of their exponent laws. Yeah. What is x cubed cubed? I'll give you two choices. Is it x to the 6th or is it x to the 9th?
X to the 9th.
X to the 9th is true. So when you have a power to a power, you got to multiply the exponents. So this is 4x minus 4x to the 9th equals 0. Now, I want to show you the wrong way to do this, okay? Do not write this down. I want to show the wrong way because I see a lot of Calculus 3 students doing silly stuff like I'm about to do, and then they wonder why they get problems wrong. So here's what not to do. Please don't ever do this. A lot of students will go, oh, I'll add 4x to the 9th to both sides, and then I'll divide both sides by x. Okay. And then I'll divide both sides by 4. Okay. And then I take the eighth root of both sides, and I do have to remember a plus or minus because that is an even root. That part's true. And I get x equals plus or minus 1. So the reason why this is wrong is because you killed off some information by doing something illegal in mathematics. Does anybody see the illegal step that I did in this process?
You're not supposed to take the x out. You're supposed to do the 4 first.
Not quite. Which one of these steps? I'll label them. 1, 2, 3, 4, or 5 contains the illegal mathematical step.
Wouldn't it be 1 because you can do the zero product property?
Well, it's 1, but why is 1 bad? That is true. This is bad.
Well, you can't subtract the 4s like that. Wouldn't you have to take out the x and
No,
set it equal to 0?
Still not why.
You can't reduce the 4. Oh, I'm so sorry.
I apologize.
I'm sorry, you can't reduce the exponent, right, by dividing?
Why not? I'm glad we're having this discussion right now because this is good. Because here we are in Calculus 3 and there's some algebra things that still have some gaps of knowledge. So
is it the 4?
It has nothing to do with 4s. Like, I don't care. Like, let's say those 4s were 5s. I don't care. Or 10s or 100. I don't care. what's illegal here is when you divide both sides of an equation by 0, it's bad. And since we don't know what x is, we are potentially dividing both sides of an equation by 0. And division by 0 is not okay. Does everybody get why this is bad? I should maybe put a true false
Yeah.
question in a future quiz, or maybe I'll put this on the final. What do you think?
But I mean, like you can't divide by 0 because it becomes out as undefined, right?
Right. So the reason why this step that I did is not okay is because I'm potentially dividing both sides of an equation by 0. So don't do it this way. So I got that a couple of you know the correct way to do it, but I wanted you to explain to me why this way is the wrong way. Okay, I'm going to erase all this because this is trash. Okay, don't do it this way. When you're solving a polynomial equation, any polynomial equation, whether it's second degree, third degree, fourth degree, fifth degree, this happens to be a ninth degree polynomial equation, never try to like divide both sides of the equation by a variable. It's like not okay, unless you could prove that it's okay. And this was not okay. So what you do is you factor and apply the zero product property. You certainly can't use the quadratic formula on a ninth degree polynomial equation because quadratic formula only works for second degree polynomial equations. So the only thing that you have at your disposal, the only tool in your toolkit is factor and apply the zero product property. I call it the ZPP for short, zero product property. So I factor out the GCF. And then I noticed that what? Well, the other factor looks like it's going to be that. And then when something times something equals 0, this is the ZPP in action, you are allowed to individually set each of the factors equal to 0, because that's what has to be true. One or the other of those factors is 0. And now when I solve for x, I get one of the answers is x equals 0. And I think we already did this one where we took the eighth root of both sides with a plus or minus. And we got x equals plus or minus 1. So we have 3 answers. And it turns out there's going to be 3 critical points. So what are the critical points? We know what the x coordinates are for 3 of them here, but we don't know what the y coordinates are. So how do we get it?
Substitute into the other equation?
Yeah, you can substitute it into either of the 2 original equations, although a smart route way to do it is remember that you already solved for y in terms of x back here when you were using your substitution method. Just use that. Since y is equal to x cubed, if x is 0, then y is 0. When x is 1, 1 cubed is 1. When x is -1, -1 cubed is -1. So boom, I got all 3 critical points. Yay. Now what? Go form your D quantity and go do your D test 3 separate times. So D, which is fxx multiplied with fyy minus fxy squared, is going to be what? Well, fxx, when I take the partial with respect to x of 4y minus 4x cubed, I get -12x squared. So there's my fxx. My fyy is -12y squared minus fxy is 4. And then I square it. So this looks like 144x squared y squared minus 16. That's the D. So now if I test 0, 0, so D evaluated at 0, 0 is going to be 0 minus 16, which is -16, which is negative. I get a saddle point. And it turns out the saddle point is located at the point 0, 0, 0. And how did I get the Z coordinate? I just plugged in the point 0, 0 into my original function representing the surface. Now when I test 1, 1, D evaluated at 1, 1 is going to be 144 minus 16. I don't even care what it is. It's positive. Yay. Then what? Well, when D is positive, you are required to test your fxx at the same critical point. And this is going to be a negative number. So then what? When D is positive and Fxx is negative, you have a relative max at the point 1, 1, and the actual relative max value is 2. So that 2 is the actual relative max value. And then when I test -1, -1, I still get 144 minus 16, which is positive. And Fxx evaluated at -1, -1 is still, still negative. So that's another relative max. So you have another, can you have two relative maxes? Absolutely. You can have multiple, infinity maximums. And so that has an ordered triple of -1, -1, 2. And we're done with this problem. The answer is the only extrema we get are two relative maximums for this guy. Okay, so any questions for this one? I hope you learned something here. For one thing, I hope you are getting a little bit of a handle on solving polynomial equations. So if I graph this, where I go z equals 4xy minus y to the fourth minus x to the fourth, and let's see what happens when I graph this guy. Ooh, oh wow, look at that. I think this is upside down. Ah, there we go. So I hope you can see that we do have a couple of relative maximums there. That's what it looks like is happening. Interesting. Let's do a different color. Bars. Whoa, that looks really pretty. How about candy bars? Nope. Candy stripes. Anybody for candy stripes? Nah, that doesn't make any difference. Okay. All right, I'm going to do one more and then you guys are going to try one. So this one I'm going to do is really kind of wacky. So please try not to freak out. Okay. I get students like, oh, it's really hard. Oh, tears. And it's not that bad if you kind of think about some mathematical truths. Okay. So we have an exponential here instead of polynomial function. E to the E is getting raised to a polynomial. Oh my God. All right. So we're going to get the partials and we'll simultaneously set the partials equal to 0. We're going to get a hell of a nonlinear system. You'll see. So when you take the derivative of an exponential, e to the u, remember the derivative is e to the u times u prime, where u prime is going to be the derivative for this first case with respect to x. So you're going to have e to the, and if you don't mind, I'm lazy right now. I'm going to go e to the blah, 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 which is that entire x squared minus y squared minus 2x minus 6y minus 3. I'm going to call that blah, blah, blah. And then when you take the derivative of that polynomial with respect to x, you get 2x minus 2. Okay. And I'll set that equal to 0. And then when I do a similar thing for the partial with respect to y, I get the derivative of blah, blah, blah with respect to y is -2y minus 6 times e to the blah, blah, blah. Okay, fine. So this is a nonlinear system of equations. Oh my goodness. Now, I'm going to apply the ZPP right now to both of them. So for the fx, if something times something equals 0, what does that mean? It means 2x minus 2 equals 0, and or the exponential to the blah, blah, blah equals 0. Well, what you should know from algebra and pre-calc is that exponentials never are equal to 0, okay? They're always positive. So this is impossible. In other words, there's no solutions. So what does that mean? Well, 2x minus 2 could equal 0. And that occurs when 2x equals 2 or x equals 1, okay? And you do a similar thing with the fy. You honor the fact that the exponential can never be 0. So what about the other factor? Well, that could be 0. So -2y equals 6, y equals -3. So what do we have here? We have one critical point, 1, -3. Ooh, okay, great. And then what? Well, now you got to go form the D quantity and do the D test. Oh dear. Okay, this is where it's going to get kind of gross. So let's do these partials separately because, that's where these tiers are going to start. But it's not bad if you just think it through, okay? fxx, okay. Fx is a product of 2x minus 2 and that horrible exponential. You're going to need the product rule. So applying the product rule to get fxx, I have, well, the derivative of 2x minus 2 with respect to x is 2 times the exponential times e to the blah, 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 plus the 2x minus 2 multiplied by the derivative of that exponential. But we already know the derivative of that exponential with respect to x because we did it before. It's 2x minus 2 times e to the blah, blah, blah. Okay, there we go. That's fxx. Now, what about fyy? Product rule. Yeah, do the product rule on fy. So you're going to do the derivative of negative 2y minus 6 with respect to y. So you'll get negative 2 times the exponential e to the blah, 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 plus the negative 2y minus 6 times the derivative of the exponential with respect to y. But you already know that's negative 2y minus 6 times e to the blah, blah, blah. Fine. Now, finally, get fxy. Good news, you don't need the product rule. You just go, okay, 2x minus 2, since I'm differentiating with respect to y, that looks like a constant multiple. And then take the derivative of e to the blah, blah, blah with respect to y, which we know is negative 2y minus 6 times e to the blah, blah, blah. Okay. Now, when I evaluate d at this critical point of 1, negative 3, so I'm going to have to basically plug it into the fxx, multiply that by the fyy evaluated at that point, and then subtract the fxy evaluated at this point squared. Now let's just think this through. Look at fxx. If you plug in the point 1, negative 3, do you see that this second term, when you plug in a 1, 2x minus 2 goes to 0? So all you have left is the exponential. You have 2 times e to the blah, 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 whatever those numbers are when you plug in 1 times negative 3. And that's going to be something positive. Times, when you evaluate your fyy at this critical point, the second term gets killed off. So you only have that negative 2 e to the blah, blah, blah happening. Fine. Minus, and then when you plug in 1, negative 3 into your fxy, the whole thing is going to go to 0. Okay, fine. So who cares? Well, remember, exponentials are always positive. So what we're going to have here is we're going to have 2 times negative 2, which is negative 4, times e to the twice blah, 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 blah. And this is a positive. So this is going to be just a negative number. Remember, we don't really care what the value is. We just care if d is positive or negative. Who cares what it is? And that means I got a saddle point. Yay. And I'm not going to do much more to that. Okay, you can go figure it out. But we're done here. So what's the moral of this story? This is a function of two variables that it isn't one of those cute little polynomials. So it's a little bit trickier. It's an exponential. And so you have to do a little bit more work to get some of these partials. And of course, but using your knowledge of ZPP, zero product property, and exponentials, you can make it all work out mathematically. Okay? So there's my mathematical argument about saddle point. Now, do all exponential functions only have saddle points? Oh, no, no, no. I can come up with another exponential function, e to the something or another, and I might get a max or a min. You never know. You got to be careful. Okay, you guys are up. It's your turn. So I'm going to put you in a breakout room with a buddy. And you and a buddy are going to try, and this one's not very hard, okay? But the ZPP will come into the conversation. So don't ever forget that because it's definitely helpful. So you're going to find all the relative extrema and any saddle points. For this function, it's not too hard. It's a polynomial, so we're good. So let's see here. I'll do 5. And when I put you in the room and you join it, turn your mic on so you can talk to your buddy, okay? I'll come visit to see if you're stuck. Good luck. Hey, Sebastian, you're late. We missed
Oh,
you. Are you okay?
yes, hi. Yeah, sorry. I had to pick up my cousin. I had to drop my little cousin off at a field trip he had today, so I kind of made it a little late than I thought.
Okay, well, I guess better late than never. We're
Yeah,
working on a problem right now, so I don't want to put you in a breakout room because you'll have no idea what's going on.
right.
So just to let you know, we were doing some more the D test where you are given a function and you have to figure out if there are any maximums, minimums, or saddle points. And they're
Okay.
working on a problem right now. So I encourage you to watch the video when when I post it later today for the first half of the
Yes.
class, so you're not totally lost.
Yeah,
Okay.
definitely.
All right, no worries, no worries. I'm going to be closing out the session for the breakouts soon,
Okay.
so just chillax for a little bit.
Sounds good.
All right. Mhm. Okay, so I was going around the breakout rooms and I was noticing that most of you are on the right track. It is a little bit tricky when you first have to do one of these on your own, but that's why I wanted to have you try it here in class. Okay, so the correct answer ends up being there is a saddle point at the point 001, and there's a relative max at the point 4/3, 4/3, and the maximum value is something really wacky, 59/27. So I'll do this problem right now and point out some pitfalls. So if you got your fx and your fy, I got negative 3x squared plus 4y for my fx, and for my partial with respect to y, I got, whoops, yeah, 4x minus 4y. Does that look right?
Yes.
Okay, I simultaneously set the 0 and I get a system of equations that's nonlinear. Nonlinear because this one term here has a squared in it. So that makes the entire system nonlinear. Now, because we're going to use the substitution method, although you could add these two equations together and kill off the y, but then you're going to end up with a quadratic anyway. So I'll just do the substitution method. I like to pick the easier of the two equations to solve for one of the variables. That's just how I roll. So here, if I solve for x or y, it doesn't even matter. I end up with x equal to y, or y equal to x, your favorite flavor. It doesn't really matter here, whichever one works. So if you chose the, well, let y equal, or x equal y, then when you substitute into the other equation, you get negative 3 y squared plus 4y equal to 0. Folks, this is a quadratic equation. You could use the quadratic formula, although that would be over killing it because this is pretty easy. Instead, I'm going to factor out a common factor, which is y. And then the other factor is going to look like negative 3y plus 4. Then I apply the ZPP, which says if something times something equals 0, I can set the factors equal to 0. Now this one I already have a solution. There's nothing to do there. Hey, y equals 0, yay. Although I get a lot of students who say, or at least a lot of my algebra students go, well, 0 doesn't count. Let's just throw it out. No, 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 no. 0 is a wonderful number, and that definitely counts as one of the y coordinates of the solution. And now this guy, if you say add 3y to both sides and then divide both sides by 3, you get y equal 4/3. Now, folks, these are the y coordinates, or if you solved it for x, the x coordinates of your critical points. So this is what I have so far. I have two completely separate critical points. One of them has a y coordinate of 0, and the other one has a y coordinate of 4/3. So I got to go get the x coordinates. Now, you can either plug the y values back into the one of the original equations, or you can use the fact that, hey, we already solved for x in terms of y. X is the same as y. Cool beans. Does that always happen? No. But here, if y is 0 and x is the same as y, we got 0, 0. And when y is 4/3, x is the same. So x is also 4/3. So these are the two critical points right here. There you go. You got them. And if you at least get your critical points when you're doing one of these problems, I do give some partial credit. So I'm so happy you were able to get the solutions to the nonlinear system. I give you something. Now, do the D test. So now you got to get your D. So what's fxx times fyy minus the fxy getting squared? Well, when I get my second partial fxx, I just get a 2. And then fyy is 6y. And then fxy is negative 3. So I square it. So my D is 12y minus 9. So let's say I want to test the 0.1. Oops. Sorry. Am I doing this wrong? Yes, I am. I'm sorry. I'm really blowing this here. I'm looking somewhere else and copying something else down. I apologize. Wrong problem. Well, you guys didn't say anything. Now, so, like, what the heck? Sorry, negative 6x is the correct fxx. Negative 4 is the correct fyy. And then fxy is 4. So this looks like, sorry, 24x minus 16. There's my D. Let's test the point 0, 0. When you plug in 0, 0 into your D, I get 0 minus 16, which is a negative number. So if you check the theorem, when your D is negative, it doesn't mean you have a rel max or a min. You have a saddle point. And so the point 0, 0, 1, I believe, is your saddle point. And then if you test the other point, which is the 4/3, 4/3 guy, you're going to get a positive value for D. In fact, you'll get what? 32 minus 16, which is 16, which is positive. Then what? That doesn't tell you anything yet. It just means that you do have a max or a min, but you're not sure which until you evaluate your fx at the point. So when you evaluate fxx at this point, let's see, I get what? Negative 6 times 4/3. I don't even care what the number is. This is clearly a negative number. And so when D is positive, but fxx is negative, you have a relative max. And it turns out the maximum value is not pretty. It's 59/27. Okay, so did you guys get this? I know at least one group did get the final answer. Did anybody else complete on this one? I'll check the chat. Say yes if you did. Yes, there's one yes. Yes. Yes, yay. Somebody? Anybody else? Nobody else got it? Come on, guys, that's it? The rest of you didn't get this right? Oh, no. Okay, Kimberly, we got one over here.
Get that far.
Oh, you didn't get that far. Oh, okay. I stopped you too short, huh?
Yep.
All right. Sorry about that. I didn't realize you needed some more time. Yeah, these do take some time to do. But the more practice you get, the better you'll get. just a matter of moving forward. Okay, so I'm going to show you to finish this out before we get to the word problems. Oh yeah, you're going to have word problems. What? Well, you know, when you took Calc 1, do you remember when they did optimization that after you learned how to find maximums and minimums, they had word problems where you had to find maximums and minimums? Yeah, and we're going to do the same thing here in Calc 3. Yeah. Is that going to be on the exam? Yeah. That's why you got to study over the spring break. Okay. So I want to show you where the second partials test fails. And that's when your D ends up being 0. Does that mean that there are no extrema? No, it just means the test fails. That's all. So let's take a look at this function, which is kind of a weird function, x squared times y squared. And let's go get its partials. So fx is 2xy squared. We'll set it equal to 0. Fy is 2x squared y, set it equal to 0. Now, when you use the ZPP, it looks like the 0.00 is a critical point, but I claim there's a lot more. There's actually infinity critical points. Why? Well, if you let x equal 0, and y could be anything, y could be any number at all. When you plug that into both of these partials, do you see that both of them go to 0? So it turns out the line x equals 0, all those infinity points that, like, here's the xy plane, okay? If you graph the line x equals 0, which is basically the y-axis, all of the points that live on the y-axis, and there are infinity of them, those are all critical points. And then further, if y is equal to 0 and x is equal to anything that you want, you also have more critical points. So this line right here are more critical points. So there's a lot of critical points. So what? Well, if you were going to try to do your D test, so you're like, okay, let's go get D. Fine. So what is fxx? Well, it's 2y squared. What is fyy? That's 2x squared. Minus fxy, I get 4xy, and then I'll square it. Okay, fine. So this looks like 4x squared y squared minus 16x squared y squared. And those are like terms, so might as well collect them. Negative 12x squared y squared. Fine, here's your D. Now what? If you evaluate D where x is 0, and I don't even care what y is, I claim you're going to get 0. And if you evaluate D at who cares what x is, any number you like, and y is equal to 0, you also get 0. So the test is inconclusive. The D test doesn't give you any information if D is 0. So what of it? It turns out there are infinity minimums. Whoa, what do you mean? Well, if I go back to my graphing software here, I'm hoping this will graph it kind of nicely. It probably will graph it better than I can. So let me just try and graph this surface. Z equals x squared y squared. Check it out. What do we got here? Whoa. Okay, you can kind of see in there. Let me, hold on a minute. You got rain gutters, okay? So if I could kind of sneak in there and see it, I got to stop it right there. Can you see in there that the on the x-axis there and the y-axis, there's a gutter, a rain gutter, and same over here if you could see it. It's kind of hard. You got to like sneak a peek inside there. Ooh, that's kind of cool. Wow. Now, if you're still confused, like I don't see any minimums, I don't know what you're looking at. I'm blind to this fact. All right. I will try to graph more of a portion of the surface for you, so you'll maybe see that there's rain gutters. There's these minimums. So I'll do my best here. I'm not that good at. I'm not a graphic artist, but I've gotten better over the years. Okay, so here's your rectangular coordinate system. So the entire x-axis is a minimum. So you kind of have a rain gutter going along the x-axis there. And then the entire y-axis is a minimum also. So you kind of have another rain gutter in that direction too. Does this sort of make a little bit more sense there? Can you see that you kind of have minimums there?
Yeah.
Yeah.
Mm-hmm. Yeah, so even though the d-test gives us no info, that doesn't mean we don't have extrema. We've got infinity minimums because there's rain gutters in the x and y axes directions there. Kind of cool, huh? Cool looking surface. Love it. Here's a problem that's super easy that I give to my business calculus students. Even they do this stuff. Business calculus students do functions of more than one variable, and they do the d-test. Yes. You'd be surprised that business calculus students have to do not only single variable calculus, but a little taste of multivariable calculus is what you're doing right now. Multivariable calculus. Functions of more than one variable. So I've given this one to my business calculus students. And if they can do it, you can do it. It's super easy. Check it out. Determine if there's a relative min, a relative max, a saddle point, or insufficient information. Determine the nature of the function fxy at this critical point, x naught, y naught. If you're given that fxx is -3, fyy is -8, and fxy is 2 at the critical point. Well, knowing that d is this, and you know you already have a critical point in hand, so, and they told you what the values are, all you do is, you substitute. Okay, so I get 24 minus 4 is 20, and that's positive. So what do I have? Do I have a max, a min, a saddle point, or I don't know yet? So what do I have?
A relative max.
Why?
Because when you tested, you did the d-test, you have 20 is greater than 0, and then when you test the second partial of x, the -3 is less than 0. So according to the theorem, I don't know if it was a theorem. Yeah,
Yeah,
it's a
it
relative
is.
max.
You're right. It's the theorem. Very good. So given this information, you do have enough information to tell you've got a relative max on your hands. Okay. Does everybody see this easy problem? This could be like a true false type of situation question. I don't know. Think you can handle it? Okay, questions so far? Okay, I'm going to do a really hard problem that you'll see similar to your My Math Lab. Okay, this is going to yield a very challenging nonlinear system of equations. Challenging in that students choke when they're actually getting the solutions. So it's not like any of the previous problems in this lecture. So we're going to finish out the section with this grand finale, and then I'll probably have time for at least one of the word problems. Yeah, you got word problems. Got to know how to do them. Okay. So here's another function. Are there any extrema or saddle points? Or maybe both. Cool. Okay. So first up, get the partials, set them equal to 0, solve the system, get critical point or more than one critical point, and then do the d-test. How hard could this be? Well, the system is really tough. Like, this is not what you're going to see in a pre-calc class. I wish they would. It would be great if the pre-calc would solve some of these really nasty nonlinear systems. But having taught pre-calc myself, they usually stick to conics, equations that are like hyperbolas and parabolas and ellipses and circles, and they don't venture out into the deep, dark world of other stuff, other curves. Okay, which is sad, but whatever. All right, so let's get the partials. So when I differentiate with respect to x, I get, well, the first term goes to 0. So the second term is a -6xy. And then the second to the last term, I get -6x. And of course, I'll set it equal to 0. Fine. The first partial with respect to y, let's see, I get 3y squared minus 3x squared minus 6y equals 0. That's a 6. Boy, that looks terrible. All right. So here's your system, and it's very nonlinear. Let me tell you what makes this system harder than the previous problems we've done thus far. You see this term right here, the xy term? That's like the rotating term. That makes it nasty. It's definitely a nonlinear term, and it makes this whole system a little bit tricky to solve. Okay, so you're gonna want to use the ZPP all the time. Like the ZPP is gonna save your rear end. Like seriously, just use it a lot. Well, what do I mean? ZPP, zero product property. Sometimes something equals 0. One of those factors has to equal 0. So, factor and do the ZPP. So I'm going to do that for the very first partial. If I factor out the common factor of negative 6x, the other factor is y plus 1, and that equals 0. So when I apply the ZPP, zero product property, which says if something times something equals 0, negative 6x equals 0, or the y plus 1 equals 0, or maybe they both do, but you can't be assured that they are at the same time. So for the first thing, when you divide both sides by negative 6, I hope you see that x is 0. Now careful, here you get y equals negative 1. This is where students choke. They wrongly combine these two puppies together. They go, oh, 0, negative 1 is a critical point. Actually, 0, negative 1 is not a critical point. So I'll just put careful here. 0, negative 1 is not a critical point for this entire problem. Well, how do you know? How do you know? I think it is. Think. When you're solving a nonlinear system, the point that you get has to make both equations simultaneously go to 0. Now, while the point 0, negative 1 would indeed make the first partial go to 0, try plugging it in to the other partial. I guarantee that you won't satisfy that equation. So please don't do something like this. You'll end up in a world of hurt. Always check your answers when you get a solution to a system. You always can check it. It's got to make both of the equations in the system equal to 0 simultaneously here. Or if they weren't equal to 0, something else, for those of you who are taking linear algebra. You always can check your solutions. Okay, well then what is the critical point or points? Hold on to your horses, we're getting there. Okay, what you're going to do is you're going to one by one test these two possibilities. If x equals 0, you're going to test it. Plug it into fy. So we're going to substitute into the other partial. What happens when we substitute x equals 0 into that partial? What happens? Well, we get a quadratic equation, 3y squared minus 6y equals 0. And we're going to use the ZPP again. Oh yeah, I'm going to factor out a common factor of 3y, and the other factor will be y minus 2. And then I'm going to do the ZPP again. So 3y had better equal 0, or y minus 2 equals 0. So I get two answers here. Okay, so what of it? So what this says right here, Fokarooskies, it says that the point 0, 0 is a critical point, and when x equals 0 and y equals 2 is a critical point. So these are two critical points right here. But wait, there's more. We're not done. I claim there's two more critical points. Oh my God, can you have that many? Oh yeah, you can have infinity critical points, as we saw before. So what I'm going to do now is I'm going to check the other possibility, which is what if y is equal to 1? We're going to substitute that into the fy and see what we get. So if I look at my fy and I substitute a 1 in place of y, oops, no, 1 everywhere I see a y. There's a couple places where I see a y here.
Isn't it negative 1?
Oh, negative 1, thank you. Negative 1, trying to go too fast here. Negative 1, negative 1. -1. Okay, what happens? So I get 3 minus 3x squared minus a minus 6. Equal to 0. Well, I can solve for x here. I can add 3x squared to both sides. And then I get 3 plus 6 on the left is 9. Divide both sides by 3. And then square root both sides. What do you have to remember when you square root both sides?
Plus or minus.
Yeah,
Plus
if you
or minus.
don't, trust me, I'm gonna test you on from now and forever. I'm gonna test you on every quiz and every exam. And if you fail this little thing where you don't see square rooting both sides or even rooting both sides gives you plus or minus, you're gonna lose it. Okay. So I get two answers, plus or minus square root of 3. What does that mean? Well, remember we were testing when y was -1. So when y is -1, there's two possibilities that x could be a square root of 3 or a negative square root of 3. So we have two more critical points. Oh my God, these are so many. Ugh, do we have to test all of these? Yeah. Yeah, you're going to have to test them all. Well, really? Yeah. Like for reals. Like, well, I don't want to. Well, I feel your pain. But you need to. Well, what do you mean? Well, you're going to go get D, and then you're going to test D 4 separate times. So your D test needs the D. So my fxx would be what? -6y minus 6. My fyy would be 6y minus 6. I think that's right. Minus fxy. So I'm going to take the derivative with respect to y. I get that. Okay. So I'm going to let you guys do the rest. So you will have to do the D test 4 times. Once for all of these critical points. You've got 4 of them here. You've got 0, 0, 0, 2, square root of 3, -1, and negative square root of 3, -1. So the final answer after, I'll let you do all this. And here's what the final answer should be. You have one relative maximum at the point 0, 0, 1. And then you have 3, count them, 3 saddle points. Is that even possible? Oh, yeah. And the order triples are 0, 2, -3. And then those other guys that had plus or minus square root of 3, they all had the same z coordinate for them. So that gives you the order triples for the saddle points there. Okay. That's a cool problem because, well, it's hard. And you got a lot going on. So there you have it. So, you got to be careful when you're solving a nonlinear system that the ordered pairs you get are true solutions, that they make both equations satisfied. Okay, any questions on this? It's pretty hellacious. Okay. No questions. All right. So what's next here? So the next thing we have here are word problems. Like so. I'm going to do an easier one, and then I'll do a harder one. So let's look at the profit one, because my business calculus students can do this one. So if they can do it, you can. Okay. So I love these kind of problems because they are applicable to real life. So I'm going to do this word problem. Well, this is easy, folks. Yes, you're going to have something like this on a quiz or exam. Yes, definitely. It's not that bad. So they're telling you this profit model here. It looks like this. That's how much profit you make if the company is selling 2 different products. They're selling X units of product A and Y units of product B. So, companies like to maximize their profits. So that's the goal. So try to find the production level for both products that maximizes the profit and then actually give the max profit. And this problem is pretty easy, as you'll soon find out, because like I said, my business calculus students, I've given them this problem, and if they can do it, you can do it, because they're not that strong mathematically. Okay. So first up, you got to get the partials, the partial with respect to x and the partial with respect to y. So px and py. So my partial with respect to x is 8 minus the 0.001 times parentheses, and then the derivative of what's inside parentheses with respect to x is 2x plus y. And I'll set that equal to 0. The other partial with respect to y is 10 minus that 0.001. And then the stuff inside parentheses, when you differentiate that with respect to y, I get x plus 2y. Okay. Now, folks, this is a linear system of equations. Why is it linear? Because the x and y that you see in both equations are just raised to the 1 power. So that's linear. What I don't like decimals because it annoys me. So I'm going to multiply both sides of both equations by 1,000. Both, and that will kill off the decimal. You don't have to do that. It's up to you how you want to roll. When I do that to the first equation and then rearrange it, I get 2x plus y is equal to 8,000. If you don't believe me, check it out. The other equation, after multiplying both sides by 1,000 and then rearranging it a little bit, I get x plus 2y equals 10,000. So this is a linear system of equations, and you can do the solution by the algebra way that you did probably then elimination method. So I'm going to multiply the second equation. I'll call it like here's equation 1 and here's equation 2. I'm going to multiply equation 2 by -2, and then I'll add it to equation 1. So I'm just going to copy down equation 1 here. And then when I multiply equation 2, both sides, of course, by -2, it then looks like -2x minus 4y equals, negative 20,000. And then I put a line there, and I'm going to add these two equations together because it'll help me eliminate the x variable. So when I add these equations together, 2x plus -2x eliminates the x's, y plus -4y is -3y, and then 8 plus -20,000 is -12,000. Woo! And divide both sides by -3, and I get y is 4,000. Now, how do you get the x? Because remember, you got to have an ordered pair. So you can substitute this back into one of the original equations that you got to help get the corresponding x coordinate. And so when you do that, and then subtract 4,000 from both sides, and then divide both sides by 2, I get x is equal to 2,000. So folks, the critical point is the ordered pair 2,000, 4,000. Now prove to me this actually maximizes profit. It actually is going to end up maximizing profit, but prove it. How do you know it's not a minimum? So if I get the second partials, oops, I went too far. I don't know what happened there.
And you're going down.
Went too far. Okay. So if I get my second partials and I go, okay, D is equal to PXX, PYY minus PXY squared, my PXX is negative 0.001 times 2. So that's a constant. And then my PYY is negative 0.001 also times 2. And then minus, and then my PXY is simply negative 0.001. It's also a constant. So what happens here is your D is going to be positive. You can check me out on this. But PXX is negative. So we do indeed, we have profit is maximized at the point when you are producing 2,000 units of product A, because that's what X was representing, and 4,000 units of product B, whatever that is. Now, the actual profit you have to evaluate your profit function at the point 2,000, 4,000. And keep in mind, profit is in terms of money. So when you punch this all in, that's a 4, not a 9. My 4s and 9s look terribly similar. Minus, etc. I'll just say, plug it into the original function. I get 18,000, and that's 18,000 bucks. So the profit is 18,000 when you're producing 2,000 units of A and 4,000 units of product B. Yay! And that's a nice business economics application for optimization. So that's all I got today. And congratulations, we're done. See you later.
Thank you, Professor.
Hey, you too.